Hello everyone. Let's optimize some functions. So let's find and classify critical points of various functions. So our first example is f of xy is equal to x to the power 4 plus y to the power 4 minus 4xy plus 1. So the first thing that I like to do in find and classify critical points is to compute all partial derivatives of first and second order. So if you start with f of x, so f of x here is going to be equal, voyons, mon truc marche mal, all right, go. Okay, so f of x is equal to 4x cubed minus 4y. Then if you compute f of y, you're going to get 4y cubed minus 4x. And now this is for the first order partial derivatives. So now if we compute the second order, so if you compute f of xx, so if you differentiate f of x with respect to x again, you're going to get 12x squared. If you compute f of xy, so if you start with f of x and you compute its derivative with respect to y, you're getting minus 4. If you compute f of yx, so if you take f of y and you differentiate it with respect to x, you're going to get minus 4. Again, this is always a good moment when these two partial derivatives are equal. So I strongly suggest, as usual, that you recompute these partial derivatives, f of x and f of y separately, because if they are equal, chances are that you've done all the computations correctly. And then f of yy. So for f of yy, you take f of y and you compute its derivative with respect to y again, you're getting 12y squared. So all partial derivatives of first and second order are computed, and all of them will be needed, okay, to find critical points and classify them. All right, now let's find critical points. So to find critical points, what you need to do is you need to set up the first order partial derivatives and you need to put them equal to 0. And this will create two equations. So I'll call the first one equation 1 and the second one equation 2. And typically what you want to do is use one of the two equations and manipulate that equation to find some algebraic condition that you can substitute or plug in the next equation. So here both equations are fairly the same, so I'm just going to use equation 1 here. So with equation 1, I'm going to isolate y, so I'm going to write that y, 4y is equal to 4x cubed, so y is equal to x cubed. So by setting it equal to 0, I just brought the minus 4y on the right side, divided by 4, and now I have an algebraic condition. I know that y, the y coordinate of my critical point needs to be equal to the first coordinate squared. Okay, so now I'm going to plug this in the second equation. So now if you look at the second equation now becomes the following. So I have 4y cubed, but now I know that y is x cubed. So I get 4y, which is x cubed now, cubed minus 4x is equal to 0. So if you go 4x cubed, so you need to multiply here the exponent. So you get 4x9 minus 4x is equal to 0. So I need to find solutions. So I can factor by 4 and by x. So you get 4x that I factor out, leaving behind x8 minus 1 equal to 0. This will induce two solutions, either 4x is equal to 0, and this gives you your first x value, which is x equal to 0. And of course, with x equal to 0, because we know what the y is, it's 0 cubed. So y is going to be 0 cubed, which is 0. So this means that our first critical point is 0, 0. Now for the second one, I know that x8 minus 1 is equal to 0. So x8 is equal to 1. So now if you compute the 8th root, be careful with even powers. You're going to get two solutions. X is equal to plus or minus 1. So this will give you two possible x values. So for x equal minus 1, you're going to get y is equal to minus 1 cubed, which is minus 1. So you're getting another critical point, which is minus 1, minus 1. And finally, for x equal 1, so same thing here. For x equal 1, the y value is 1 cubed. which is 1. So your last critical point is 1, 1. So we get 3 critical points, 0, 0, minus 1, minus 1, and the third one, 1, 1. Now it is time to classify those critical points. So let's start with the first one, 0, 0. So for 0, 0, you compute the D number. So it's D 0, 0. So it's f of x, x. So it's 12 times 0 squared times 12 times 0 squared. So that's f of y, y at 0, 0 minus f of x, x at 0, 0. But here it's a constant function, so you get minus 4 squared. So you get something negative. So automatically here, we can conclude that 0, 0 is a saddle point. Yay, you can write the function at the origin. Okay, so now just rinse and repeat here. So for, let's say, minus 1, if you compute D at minus 1, you're going to get 12 times minus 1 squared times 12 times minus 1 squared minus 4 squared. And that number is actually positive. If you compute it, you get 144 minus 16. And then what I do is I need the sign of the f of x, and this is also positive. It's just 12. So you can conclude using these two signs that the point minus 1 is a local minimum. Here we go. Yay. Now for the last one, so this is very similar than the previous one. So boom. So for the last one, so for 1, 1, the only thing you have to do is compute the D number at 1, 1. So the D number at 1, 1 is going to be 12 times 1 squared times 12 times 1 squared minus 4 squared. This is again going to be strictly positive, and again f of x is going to be positive, so 1, 1 is also a local minimum. So that's it for classification. You simply have to compute the D numbers, look at the sign, and look, if needed, when it's positive, look at the sign of f of x to make your correct conclusion. All right, for that example, that's it, that's all. All right, our next example is we want to maximize a production function that depends on L and K, where L is the amount of labor and K is the amount of capital that you need to produce stuff. Okay, so, and the actual function is 216L squared minus 16L cubed plus 189K squared minus 9K cubed. So let's maximize this, which means let's find critical points and let's find a maximum in there. Hopefully, if not, we're not going to maximize anything. So again, the way I like to do these questions is by first computing all partial derivatives, first order and second order. So if you compute PL, so if you differentiate with respect to L, you get 400 and L times L minus 48L squared. Because I know I'm going to be using this equation to find critical points, might as well simplify it. So here what I did is I factored by L, leaving behind 432 minus 48L. And I also computed the other one, so PK. So you're getting 378K minus 27K squared. Again, I factor by K, leaving behind 378 minus 27K. So this is going to be helpful to find the critical points. If you simplify these partial derivatives, first order, it's going to simplify your life afterwards. But anyways, I'm going to compute second order partial derivatives, might as well. So PLL, so if you take PL and you redifferentiate with respect to L, you can double check that it gives you 432 minus 96L. If you compute PLK, there's no K's in there, so you just get 0. If you compute PKL, so if you start with PK and you differentiate with respect to L, there's no L, so you get 0. Again, you're like, they're both equal, feels great. And then PKK, it's funnier en français, PKK. Anyways, you're going to get 378 minus 54K. Make sure you know how to compute those. Again, in an optimization question where you have to find and classify critical points, there's a lot of marks. just for those computations. And typically, these partial derivatives are simpler than the one you compute in a regular question about partial derivatives. Anyways, so now let's find critical points. So if we set PL equal to 0, because we factored already, we can see that it's going to happen either when L is equal to 0 or when 42 minus 48L is equal to 0. And if you solve for L, you're going to get 9. So our critical points, the possible L values, so the first coordinates are going to be either 0 or 9. And now if you set PK equal to 0, this will happen either when K is equal to 0 or when 378 minus 27K is equal to 0. If you isolate K in there, so if you divide 378 by 27, you're going to get 14. So here the possible second coordinates for those critical points are 0 and 14. So here be careful. I get a lot of people just answering, it's 0, 0, and 9 and 14. No, so the idea is that if L is 0, there's two possible K values, so it's either 0 or 14. And if L is 9, you also have two possible K values, which is 0 and 14. So this induces actually 4 critical points, 0, 0, 0, 14, 9, 0, and 9 and 14. And we're going to have to classify all those 4 critical points. Again, you're classifying 1 or classifying 4. It's not more difficult, it's just more tedious. So I've done all of them for you. So for 0, 0, you can double check if you compute the D number, it's going to be positive. And if you look at PLL, so the first partial derivative, the second order partial derivative with respect to L, you're getting something positive. So because you have that the D number is positive and the F of the PLL is strictly positive, we have a local minimum. So for 0, 14, if you compute the D number, it's going to be negative. So we have a saddle point. For 9, 0, you're also going to get a D number that is negative. So you're going to get, again, a saddle point. And for 9 and 14, if you compute the D number, it's going to be strictly bigger than 0. And then PLL is going to be now strictly less than 0. So now you have a local maximum. And this is the one we were looking for. So if you invest 9 units of labor and 14 units of capital, you're going to maximize production. Again, here, I'm going over the details, but make sure you know how to fill up the blanks. Okay, so, it's like all the computations are there, but make sure you understand all of them. Okay, so, all right, for that example, that's it. That's all. Okay. All right, les amis, it's time to maximize some profit. This is the ultimate goal, I guess, for you guys in commerce. So suppose we have 2 products, A and B, and suppose that the demand for those products are going to be labeled XA and XB, and suppose that the prices are going to be labeled by PA and PB. Of course, I'm using here the subindex to relate to the actual product A and B, respectively. Suppose that the demand functions are the following. Suppose that XA is 200 PB minus 200 PA plus 2000. And suppose that XB is equal to 200 PA minus 400 PB. Okay, so those are our demand functions. So the goal is to find at which prices should we set product A and product B in order to maximize profit. So here we want to maximize profit, and this is of course hopefully a function that you know, an equation that you know very well. So profit is always revenue minus cost. So what about revenue? So what is our revenue? So for product A, if I'm selling XA amount of product A at PA dollars, then the revenue for product A is going to be XA times PA. If you want to compute the revenue coming from product B, well, if you're selling XB of them at price PB, your revenue for product B is going to be XB times PB. So your revenue for both combined is XAPA plus XBPB. What about the cost? So we know for each unit that we produce of A, it costs $12 per unit. So the cost for producing XA units will be 12 XA. And if you're producing XB unit of product B, because it's $5 per unit, the cost to produce product B is going to be 5 times XB. And now what you have to do is you need to replace XA and XB by their equation. So we know what XA is. So we want to create a function with only two variables. Okay, so 2 is enough. So XA is going to be replaced by its equation, and XB also is going to be replaced by its equation. Now, if you do that and you FOIL, I'm going to skip over the details, but make sure you know how to do this. So if you just FOIL correctly, you can simplify the profit function as minus 200 PA squared plus 3,400 PA plus 400 PA PB minus 400 PB squared minus 400 PB minus 24,000. So this is just after foiling these equations and simplifying and canceling terms. Once I have my function, so here the big difference with this question versus the previous questions is you had to construct your own equation. But once we have the equation, now it's rinse and repeat from before. I'm going to first compute all possible partial derivatives of first and second order. Then I'm going to compute the critical points, and then I'm going to classify them. So if you differentiate the profit function with respect to PA, so if you differentiate with respect to PA, so the first partial derivatives of first order is going to give you minus 400 PA plus 3,400 plus 400 PB. And then if you compute the partial derivative with respect to PB, you're going to get 400 PA minus 800 PB minus 400. So I'm just computing the first order partial derivatives. And now if you're looking at the second order partial derivative, so if you start with del P over del PA and you differentiate again with respect to PA, you're going to get minus 400. If you take del PA over del PB and you differentiate that one with respect to PA, you're going to get 400. If you are looking now at del P over del PB and you differentiate again with respect to PB, you're going to get minus 800. And if you take del P over del PA and you differentiate with respect to PB, you're going to get 400 again. And of course, like these two mixed partial derivatives, they have to be equal. If not, you made a mistake somewhere. So I have all my partial derivatives, a lot of notation here because of big P and small p and sub A and sub B. But anyways, that's just the way it is with these questions. So now what we have to do, we have to find critical points. So remember, for critical points, we just have to set the first order partial derivatives equal to 0. So if you take the first partial derivative, minus 400 PA plus 3,400 plus 400 PB equals to 0. And then the other partial derivative, 400 PA minus 800 PB minus 400 is equal to 0. So here we have a system of linear equation. We have to solve for PA and PB. You could go and summon your stuff from linear algebra and apply Gauss-Jordan, but we're not going to go there. Actually, here, I'm just going to use elimination. I can see that if I add the first equation and my second equation, the minus 400 PA and the 400 PA are going to cancel each other. Just got lucky here. It's not always going to work out so easily. But if you add these two equations together, you're going to get minus 400 PB plus 3,000 is equal to 0. So I'm just adding the two equations together. And then if you isolate PB, so if you bring the 3,000 on the right side as minus 3,000 and you divide by minus 400, you find that PB is equal to 7.5. And then with the first equation, you can compute, if you replace PB by 7.5, you can verify in the first equation that the PA you're going to get is 16. So there's only one critical point here, and it's 16.7.5. So it's the only critical point. So now we have to compute the D number to decide if it's a saddle point, a min, or a max. Hopefully it's going to be a max because we have only one of them. Typically in the question where we are asking you to find a maximum or a minimum, if you find only one critical point, normally that's the one, but you still have to justify that indeed this is a maximum. So if you compute the D number, so if you take your partial derivatives correctly, so minus 400 times minus 800 minus 400 squared, you can verify that this number is strictly bigger than 0, so it's a min or a max. And because the partial derivative with respect to PA, the second order partial derivative del P over del PA squared is minus 400, which is negative. So because the D number is positive and the second partial derivative, that first one here is negative, you combine these two things to say that 16 and 7.5 is a local maximum, so we should charge $16. So that should be the asking price for product A, and we should charge $7.5 for product B. So that's the asking price for the second product, and this will maximize our profit. All right, so for that example, that's it, that's all. And actually for that chapter, okay, that's it, that's all. Bye-bye.